Hello, this is Brian Kinghorn, and I'm going to talk to you today about managing trait distributions in MateCell. And this is the second of 3 videos on this subject. The first one was standard operations. This is advanced operations, and you might think of it as ways to cheat in order to get MateCell to do what you want it to do. And the third one, we'll look at, should I manage my traits? So what I show you in this video may or may not be advisable for your breeding program. That's for you to decide. But one thing I would suggest is it's quite educational, and as you'll see when you go through this video, you can discover a few things about your breeding program that you might not otherwise have picked up. We're going to look at 4 examples. First of all, I'll look at duplicating trait columns and also showing separate parental inputs to histograms. We'll look at migration between farms, treating farms as traits. Then we'll treat breeds or variety as traits and look at managing breed proportions. And then we'll treat ages as traits and look at managing the ages of parents. So this is the first example, and I prepared a data set and added extra columns. This is the classic demo data set, and intramuscular fat as a trait here that I'm going to work on, highlighted. What I've done is I've copied it over in this column, and I've also got columns to show separate inputs from sire and dam. And I've placed them in this order because now we have got 3 extra traits, making a total of 9, and so the copy of intramuscular fat is down here underneath intramuscular fat, and you can see it is a copy because the histograms are identical, and on the left is the sire and the right the dam input to intramuscular fat. So how do we do that? This is the copy column, which is identical, and if we looked at these 2 individuals here, male and female, and if we mated them, then the predicted progeny mean would be the average of the 2. Over here, if we looked at this column, the average of the EBV of the sire and 0 would be represented in the progeny as half of the EBV of the sire. We just have to take a note that those histograms will have a scale which is halved compared to what you would expect to get for sire EBVs. Similarly with the dam, in this column for this trait, as MateCell takes it, the average of those 2 things will be half of the EBV of the dam. So if you wanted to represent the EBVs on the same scale, you would double these figures that I've got in these columns. Otherwise, you can just simply copy them across and accept that the scale is out by 50%. First of all, we'll look at using the duplicated traits. So for intramuscular fat, I'm going to set a minimum value at a boundary, and I'll set that at 0.8. And give it a reasonably strong weighting so we see something happening. And what we're doing is we've asked to cut off the left-hand side of the distribution, and we can do a different but similar thing. Set a maximum value at a boundary, and I'll set that at 1.3. For the same trait but in a different distribution, I'll also give that a weighting of 5 and resume. And you'll see what we are doing is cutting off the top end and the bottom end of the distribution of predicted genetic values for the progeny. And if we wait for a while and let this settle down, we can see that we can do this without a great deal of compromise. I'm not saying it's a good thing to do, but it does illustrate to you you've got the ability to act on a single trait by duplicating it and applying separate controls to it. So let's take those 2 off and look at doing something else. I will look at intramuscular fat, and there's this control here, tactical desired gains stationary. I'll set it to be approximately equal to the population mean and give it a weighting of 1. And what I'm doing is constraining for no change in that trait, which means because I've kept it where the population mean was for the good solution, we're still there. But now if I look at carcass weight and think that I want to increase the mean in carcass weight, I'll put a small weighting on that and invoke that. And what will happen is you'll see carcass weight here is moving up, while intramuscular fat is being stabilized as we've asked it to be. Additionally, for birth weight, we might want to reduce birth weight. May or may not be a good thing to do in your case. So I'll put decrease mean and have 0.2 as a weighting in that, which I've discovered previously is enough to show this. And you look at the mean birth weight's going down, the mean carcass weight's still gone up, and we've managed to maintain intramuscular fat, which was the desired outcome we had to have no change in that. And of course, this happens at some compromise. Lastly, we'll look at the value having separated the sire and dam inputs. But here we see we've got quite a bit of use of low intramuscular fat sires, And let us say in this scenario that after this breeding program, we want to have available high intramuscular fat sires for a separate operation. So this may be natural mating. So without changing desired mean, we want to increase the intramuscular fat EBVs of the sires used. So if I increase the mean in that, I'll put a small weighting on there, which I think is sufficient, 0.15, and resume. Keep an eye on this graph down here on intramuscular fat for the sire, and you'll see we're starting to get higher intramuscular fat bulls used, and this may provide you with opportunities in your breeding program beyond the current mating set, if that's what you want. And of course, the intramuscular fat in the progeny has maintained stable, and so we've essentially maintained that by putting some downward pressure on the EBVs on the female side. So that gives you an example of using duplication and separate sire and dam inputs, and we'll use this latter effect of separate sire and dam inputs in later examples. Okay, we're now going to move on to an example where we treat farm as if it were a trait, and it's going to be farm 1 and farm 2, which will give us a very simple example of managing location. This is classically something you would do using the grouping feature of MateCell, but there's some potential value in taking this approach in some cases. So farm 1 and farm 2 give us candidates through the blue lines, and these candidates, if they're used for breeding, can be used in their home farm or they can be migrated. So in the data set, I've added a trait called farm, and given like an alternate plate drop at a conference, 1, 2, 1, 2, allocating farm location to different candidates. And I've separated the sire and dam contributions to this trait farm, as I've done before, by setting the dam components all to 0 for males and the sire components all to 0 for females. Okay, here's the run. And you'll see the scale for farm ranges from 1, which is farm 1 times farm 1 matings, farm 2 by farm 2 matings, and crosses between farm 1 and farm 2 or vice versa are 1.5. We cannot separate those two crosses because trait is additive, and we'll come to that later. You will see that farm 2 sires are used more than farm 1 sires, and that's something we'll also come to later. But let's first of all put upward pressure on farm number. And when we do that, we see some compromise. What we're doing is asking MateCell to give us a solution that involves only farm 2 individuals, and there's some compromise, obviously quite a big one. Obviously, the species is fecund enough for all the matings to come from that second farm. What we can also test is go to farm 1 individuals by decreasing the mean, and we'll see when we were here, the compromise is even greater. That gives us a bit of a feel for the merits of individuals in the two farms, and we could do that separately for the different sexes and get an impression of what's going on there. I'll release that now and consider that we want to have more balance in the use of sires. So what I can do is select desired gain stabilizing, we'll leave it at the center there, and this is organizing so that we have equal use of sires between farm 1 and farm 2. The number of migrants, the migrant matings, is very high, 1, 2 or 2, 1. What we can do is increase the variation in this trait farm, and that will pull down the center and push up the outside. So if I increase variation, and I'll do that with a weighting which is quite small, like 0 to 5, which I found is sufficient to illustrate this. And that brings down the number of cross matings between farms, and that may be a target sort of level you have for how much migration you want to have between farms, enough to make some connections there. Of course, this doesn't actually give you control over whether they're migrating 1 to 2 or 2 to 1. And that's because the traits are additive and you're looking at average effects, and we cannot distinguish between the two. However, with marker management, we do have 1, 2 and 2, 1, and we do have the ability to use this in order to separate those two. And I'm not going to use that for this example. I'll move on to the next example with managing breed proportions to show that. So now we come to the example where we treat the breed of an animal as if it were a trait. And this is a Hereford Angus composite that I've simulated. And breed is a description of the proportion Angus. So 0 is pure Hereford and 1 is pure Angus. And I've allocated purebreds to the foundation animals in population. Those are the animals with parents that are unknown. And further down in the pedigree, an individual inherits the average of the breed of its sire and the breed of its dam. I've added another trait, which I call 2PQ, where P is in natural fact just the proportion Angus, for short, and Q is the proportion Hereford. So 2PQ, familiar to students of population genetics, relates to the degree of mixture. So for a purebred animal, where P or Q is 0, 2PQ must be 0. And for an animal which is a 50-50 mix, P and Q are a half each, so 2 times a half is a half, and that's an equal mixture. And that would be the case for a first cross or second cross, the second cross showing less heterosis. So 2PQ does not handle heterosis per se, just breed mixture. We will handle heterosis in a different way later in this video. So here we are making a run of that data set, and here's the trait breed, with on either side of it sire and dam contributions. And in each case we have Angus to the right and Hereford to the left. And here is 2PQ, which is our measure of mixture in the breeds. So if I aim to increase the mean in 2PQ, I will get more even mixture between Hereford and Angus. And we see that in the progeny distribution and also in the contributing sire and dam distributions. Conversely, if I decrease the mean, I am going to head towards more purebred sires and purebred dams, and we see that happening straight away. And we get a mixture of breeds in the progeny. Let's go free for a moment and look at what happens if we want to aim for a mixture of breeds purely by decreasing variation, which we can do here. We see how we're getting closer to having a 50-50 mixture of the composite, but we don't know how much of that is going to be due to heterosis versus later crosses which don't give so much heterosis. So let's look at controlling that. If I go to tactical desired gains stabilizing, go for a 50-50 mixture, I'll invoke that. Go back to high variation. If I decrease the mean in 2PQ, shall we say to 0.25, then we get a result which might be useful for some applications, as I'll describe. What we have now is an even distribution. We do have a lot of use of purebred parents, which means we're going to get purebreds here as well as largely first crosses probably in the progeny. And this is the sort of situation that could be useful if you want to market your seed stock in different categories: high grade Hereford, high grade Angus, and something close to 50-50. So purely from a marketing point of view, it might be useful to go for this distribution as well as go for more heterosis. However, in the center here, with the fact that traits are additive, we don't have the control of whether these are Hereford-Angus crosses or Angus-Hereford crosses. Let me let this go free just for a moment, illustrate something to you. And now that this is stabilized, just take a snapshot in your mind of this distribution of breed. And if I go over to market management, you'll see this distribution looks somewhat the same, and it is in actual fact identical. And this is going to be the basis of describing to you how to control the direction of crosses, Angus-Hereford or Hereford-Angus. We're going to use the marker management tab to control heterosis and indeed imprinting, because we'll be able to handle the difference between Angus-Hereford versus Hereford-Angus. The genotype probability codes that you see here are described in the manual, and what we're doing is calling Angus allele 1 and Hereford allele 2. And these codes give us, for the genotype probabilities in this case, 4 different genotypes: 1, 1, 1, 2, 2, 1, and 2, 2. And I'm going to handle this rather quickly in the interest of time, so you may want to pause this and read this slide or come back to it later. But Angus and Hereford are alleles 1 and 2. The proportion Angus is P, so this ends up being P squared, PQ, QP, and Q squared. You'll notice that P times Q is the same as Q times P, so these two columns always have identical information in there for the current trick only. That's not generally the case, but what we're doing is manipulating the marker management tool in order to give us what we want for this breed proportion. And the value you put in the box in each of these cells is the probability of two gametes giving the genotype. So an F1 cross, which is AH, has a 25% chance of getting two A gametes chosen at random. If we look here, an Angus animal, and line 274 is an Angus animal, will be 100% chance of being AA and 0 for the rest. An F1 or an F2 cross will have an equal chance of each. Even though you won't get an AA genotype in an F1 cross, this is the rule down here. So let's go back to our example. We move over to marker management and we look at the probability of being a 1-2, which is basically an Angus times a Hereford. So I'll increase the mean for that. And we can see that we have quite an impact on that outcome. We go back to trait management, we'll see we're getting Angus sire times as much Hereford dam as we can get. I go back to marker management and do it the other way around and go for increasing the mean of 2-1. We're now getting that directional control. If I go back to trait management, we see we're getting a Hereford sire over largely Angus females, so that these crosses are in that direction. What I can do is take those both off and invoke them with a smaller weighting. We look at the trait management, we'll start to see that we'll get an impact on both parental breeds, more so Hereford sires, but it's now settling down. And if we want to change that, we can go back to marker management and give more encouragement to Angus sires by increasing the weighting on this factor here. And we come to a more balanced outcome. So now we'll move along to the next example, which is managing the ages of parents. So now we're going to use the year of birth of animals and represent that as a trait. Here it is, birth year. And I've simulated this data set using PopSim, which has been used quite a bit for MateCell users looking to investigate the long-term effects of different diversity policies. In this case, I have doubled the EBV for the birth year of the dam and likewise for the sire, so that the scales will make more sense. And here they are. We can see the scales are on the same scale. Birth year in the center for the progeny and the sire and dam contributions to that. So let's first of all look at the effect of using just younger sires. If I increase the mean of the birth year of the sires, you will see the solution settling down at some compromise and gain, but a little bit more genetic diversity there. Let's now look at older sires. If I decrease the mean, we were sitting here. This will just take a little bit of time to settle down. And we'll see that there's a bit more co-ancestry with the older sires. There's more diversity in the younger ones, and that's largely because the older ones are those that have survived for a number of years in the herd, and they're probably from quite good lineages, so to speak. Let's do the same thing on the female side and look at the impact of increasing the mean to get younger females, and we won't be able to get only juvenile females because they're not so fecund. We need to have some of the older ones as well. This is a reasonably fecund species, perhaps. It might be sheep. And we can see there's only a small compromise involved in using the younger females as far as genetic gain is concerned. That's because older females have got less chance to be good because we need to keep so many of them. If we decrease the mean, we end up getting more genetic diversity. These older females give a better representation across the herd than the older males because there are more of them and they haven't been selected so hard. Okay, let's do something else with the ages. What I'm going to do is stabilize the average age of the males and the females at about the current mean. And then what I can do is increase the variance for the progeny. So what that's doing is, without making much change to the parental age averages, I've increased the variance, which means we're getting young bulls mated to young females and older males mated to older females, which may or may not be a policy that you have. Some people do these things, and this is one way of looking at the consequences of doing them. You can see some compromise involved when we're going age to age. If we decrease variation, we're doing it the other way around. We're reducing this distribution of birth year and progeny while not making much change in the average age of sires and dams. And that means that we're mating older males to younger females or vice versa. What might be more sensible is to categorize individuals as juvenile and adult and put that into the data file and see the costs of doing them. And it's for behavioral reasons that they do it, presumably some value in that, but it is useful to look at the compromises that can be made when you do these things. Okay, so that brought us to the end of this video of advanced operations. Next video, we'll look at the question of should I manage my traits and what are the circumstances under which it could be a useful thing to do without doing too much compromise in the rest of the breeding program. Thank you for listening.